Hello everyone. Welcome to today's live interactive session on geology and soil mechanics. Today is the fourth discussion session, and in the previous session, actually we studied mostly about the compaction, soil compaction. What is the mechanism involved in soil compaction? And after that, we solved some problems regarding soil compaction, and then actually we introduced the topic of permeability. Right. So we understood that what permeability is and what is Darcy's law, and we solved some problems regarding those two. So let us continue with permeability in today's class too. So first we will be discussing, revising whatever has been taught to us, and then we will be solving some simple problems. Okay. So how do we actually determine this permeability or hydraulic conductivity K? So we studied that uh, velocity is proportional to the hydraulic gradient, and then we have the proportionally constant, that K, that comes into the picture. This K is nothing but the permeability or hydraulic conductivity. This depends from soil to soil type, and also there are various other factors such as fluid viscosity, pore size distribution, grain size distribution, void ratio, etc. Those also influence this permeability. Now, for a particular type of soil or for a particular soil specimen, okay, having certain conditions, in certain conditions, how do we determine this permeability? So there are two types of tests that are generally used. One is the constant head test and other is the flowing head test. So the constant head test is generally used for granular soil. So granular soil, obviously, as you can imagine, okay, you can have a picture in your mind. Granular soil is nothing but sand. So sand, obviously, if you pour water into the sand, the water can easily flow through sand, right? So, so the loss of hydraulic gradient, okay, or the loss of head through granular soil is very fast. So in that case, always remember that we are using something where the where the test where we are maintaining the head. Okay, we are maintaining the head so that we can actually do the calculations, okay, so that we can find out the volume change or whatever we need to do. And so that's why for granular soil generally we use the constant head test. And for fine grained soil, where the fine grained soil such as clay, right, fine grained soil are nothing but clays. So for clays, what happens is actually for clays the hydraulic conductivity is generally very low. So the soil, so the water actually percolates through the soil very slowly, right? That's why what we need to do, we need to give some large head difference. Okay, we need to give some large head difference. That's why we use the this flowing head test. All right, so we use this flowing head test actually. All right, so one is the constant head test and the other is the flowing head test. So constant head test is generally used for granular soil, and this flowing head test that is generally used for fine grains. Okay. So the typical arrangement. Okay, the typical arrangement for a constant head test is shown here. So we have the soil specimen here actually. We have the soil specimen here, and we are maintaining a fixed head h. Okay, across the entry and the exit, we are maintaining a fixed head h. Okay, so this head is actually maintained at h by constantly pouring, like constantly having this water supply, right? So a fixed head h is maintained. Now we have two porous stones placed here, and between the porous stones we have the soil specimen. So what we generally do is that for a particular time t, in a particular time t, we measure the volume. Okay, we measure the volume of water that gets collected in a graduated flask. Okay, so in a particular time t, we measure the volume, measure the amount of water that flows through this flows through the soil and then gets collected in this graduated flask, right? In time t, q amount of water gets collected. So if the area flow of cross section is a, okay, a, so we can write it q is equal to area into velocity into time, right? Right, this will give us the this q value, this q, that is the total amount of water that is collected in time t. Okay, so now this v is nothing but k into I. From here you know that v is equal to ki, so v is equal to ki times t. From here, if I want to calculate k, I can easily calculate as q by a I t. Right, now k is nothing but q by a I t. Now what is I? I is nothing but the head divided by the length of flow. Okay, this length of flow L, right? So I is h by L. So if I replace I by h by L, we will get QL by AHT. This is how we find out the hydraulic gradient from a constant head test. Alright. Next, what we have is we have this falling head test. Okay, next we have this falling head test. So in the falling head test also almost similar arrangement. So we have a soil specimen between two porous stones. Okay, we have soil specimen between two porous stones, and then what? Then instead of maintaining a constant at h, right? So here what happens with time, head changes. Okay, with time the head is actually falling. Okay, the head is changing with time. So at time t1 the head was h1, and as you start the experiment after a time is elapsed, at time t2 the head is h2. So the head is falling from h1 to a2, right? So there is a head loss. Correct? There is a head loss. And how is this actually measured? This head loss is measured is using this standpipe. Okay, there is a standpipe of it. Okay, the area of cross-sectional area of this standpipe is say A. Okay, so here we are actually measuring the head that is falling. We are seeing that from this much head, this much is coming. Right, so that head that it is falling, that we are seeing from here, seeing in this standpipe. Now you can write the flow rate as same q is equal to ki a, I is nothing but h by L into a, right? H by L into a. Now this actually we can equate to minus a dh by dt. That is area of the standpipe times the gradient. Okay, gradient of flow, that is dh by dt. So in time dt, dh head is reducing, and as the head is reducing, as the head is falling, we are putting a minus sign here. Okay, we are putting a minus sign, right? And this area is the area of cross section of the standpipe, and this area is the area of cross section of the specimen. Okay, so we can write dt is equal to AL by AK. Okay, this is K minus DH by, sorry, minus DH by H. Sorry. H by H. So the time, say the time initially was 0, and then for time t, it's going up to time t. Total time elapsed from start of the experiment to the end of the experiment is t. So 0 to t, AL by AK, TH by H. H is going from H1 to H2. So T1 minus T2 is nothing but T. Okay. So if we integrate this, you will get K is nothing but AL by AT, H1 by H2. So this is the relation. So using this relation, we can determine the hydraulic gradient using a falling test. So next there are some, so as I said in the beginning, that this hydraulic conductivity depends upon various factors. So one of them is the grain size distribution, then we have the void ratio, temperature, and so many other things. Okay, so there are some relations that are given where this hydraulic conductivity is related to the detent size, right? Where is it related to detent size? So the other name of this detent size is nothing but effective size. Okay, so K in cm per second is equal to C into detent square. This was given by A.S.R in 1931. Okay, C is a constant between 1 to 1.5, and this effective size is in m. Okay, so you can see that if this detent size is increasing, obviously the K is also going to increase. Then one more relation was given by Casagrande. This K is equal to 1.4 e square. K is equal to 0.85, and also K is proportional to EQ plus 1 plus C. So you can see if void ratio increases, then K is also going to increase. So if void ratio increases, this K is also going to go up. Obviously, see, void ratio increase means what? The soil is, say, for a sand, the soil is loosely packed, loose sand. So if E is increasing, that is, the soil is becoming loose, obviously the water is going to easily pass through it. Right? So if E is increasing, K is also increasing. Okay. Now comes equivalent hydraulic conductivity. Okay. Just a second. So what does equivalent hydraulic conductivity mean actually? So say you have a, some layer of soil, okay, n layer of soil. Say. So first layer, second layer, then up to n layers. Okay, say number of soil layer. So each layer has horizontal hydraulic conductivity of KH1 and KV1. Like okay, similarly this will have KH2, KV2, KHN, KVN. So there are n layers, and all of these layers actually have different horizontal hydraulic conductivity as well as vertical hydraulic conductivity. Okay, that is the soil is anisotropic. So in both the directions, the properties are different. In horizontal direction, there is one hydraulic conductivity, and in vertical direction, the hydraulic conductivity changes. So there are n number of layers, and each of these layers have different hydraulic conductivity in the two directions. Right. Now the first case is for horizontal flow. Right. So for horizontal flows, you can imagine this in that way that say imagine like say you have some pipes. Okay, this is pipe number one, then we have pipe number two, pipe number three, then we have n number of total pipes. So each of the pipes are supplying water. See, okay, each of the pipes are supplying water. Then this total it is coming and joining a large pipe. Okay, the total flow is happening like this. So each of this pipe water is flowing, and finally they all combine and flow along a larger pipe. Okay, we can think this as like that. Now this total flow q, this total flow which is happening through this larger pipe, say that is q. Now this q we can write it as q is equal to v to h. So this whatever you're writing this flow is nothing but flow through the cross section in unit time. Okay, now this total flow comprises of the flow from all this, right? Comprises of the flow from all these small pipes, isn't it? So this we can write for each of these pipes. We will have same v into, so it is nothing but velocity into area. Okay, this height is say h. Say the diameter of the width of the larger pipe is h. Okay, say so is this h is nothing but h1 plus h2 plus hn. This is nothing but the sum of the thickness of all these layers. Okay, sum of the thickness of all these layers. This is nothing but h. So q into 1 into h. 1 means nothing but we are considering unit cross sectional area, means on the other directions. In the other directions, that is the dimensions are 1 1. Okay, unit cross section area. The cross section is unit cross section area, and this height whatever you are considering, that is h, not unit cross section area. Like on the other direction, like in that the out of plane direction, we are considering unit length. Okay, unit length, and this heights whatever that times unit length, that will give you the area, right? So h, the total is h. So this h total h multiplied by the out of plane 1, that is the area, right? Total h times 1, that is the area. So for all of these layers, similarly we can write v1 into h1 plus v2 into h2 plus dot 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 vn into hn, where v1 v2 vn, these are the velocities of flow in each of these layers, right? And H1, H2, Hn are the thickness of the individual layers, right? Now this V we can write down as KH equivalent into I equivalent, right? KH equivalent into I equivalent. Then V1 we can write as KH1 into I1. Similarly, Vn we can write as KHn into In. Now this KHN, I already told that that is nothing but the horizontal hydraulic conductivities in each of these layer. All right. Now what about I? I is the hydraulic gradient in each of these layers. Now you can imagine, say, uh, you have a number of pipes like this. Okay, just water is flowing, like your pipe is, you have held a number of pipes in your hand like this, one above another, and the water is flowing from one side to other side. Okay, or you can imagine you have hold a bottle. Okay, bottle with hollow bottle with water in it. So hollow number of bottles are stacked above one another, and you have just bend it like this. Now, this height difference, this head difference, say from a datum you are measuring, this head difference will be same. Okay, same for all the layers, right? Same, that is the hydraulic gradient. This I, this is actually same for all the layers, isn't it? This will be same for all the layers. So this will actually be same for all the layers. I's are actually equal. Okay, so therefore, what we can do, we can write it as KH equivalent is nothing but KH1 plus KH2 plus dot plus HN by H. So how did we get this? Nothing but from here. Okay, so Q is equal to this plus this. So how did we get this? So this Q we can write it as KH equivalent into I into H. You are equating it to this part, V1 H1. So what is V1? V1 is nothing but K1 I1 H1, right, plus K2 I2. Okay, so H2 plus dot KHN IN HN, right? So all these are equal. All these i's are equal, so they will cancel out. So we can get this expression, right? So this was for horizontal hydraulic conduct, horizontal flow. Now what about vertical flow? If the flow is vertical, so we consider layers are there and the flow is occurring in this direction, right? This we understood. Now what if the flow is in this direction vertically? That time what will happen? Let us see. Okay. So in that case, what is going to happen is that flow is entering here. Okay, water is entering first layer. Water is entering first layer. From the first layer, it will go to second layer. Will there be any loss of water? No, right? So the water needs to be, amount of water needs to be continuous. That is, the flow of continuity should be maintained, right? That is same amount of water is actually flowing. Flow should be obviously same. If you remember from from basic hydraulics, the flow of water should be same. Is the flow of water should be continuous, isn't it? So from the continuity equation, what we can have? From the continuity equation, all the Q's, all the flow. will be equal. That is the all the velocities will be equal. So all the velocity of flow should be equal. So V should be equal to V1, should be equal to V2, it should be equal to V3, dot 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 equal to Vn. Right. So Q flow is what? Velocity into area. So area you can neglect. So area will get cancelled out. So all these V's will be equal. Right. All the flows are equal. That means all the velocity should be equal as the area is constant. Area of flow is constant. Right. Area of flow is constant. This into the out of plane direction. This area of flow is constant. So V times the area flow, that is nothing but the V times the area flow, that is nothing but a Q flow. So the flows are same, right? The flows are same. So these V's are also equal, velocities are also equal. Now these velocities are equal. This is the first thing that we understood. The second thing that will be happening is that for the entire flow, the total amount of head loss that will be happening, total amount of head loss will be the sum of the head losses in each of the flow. Right? Will be sum of the loss of heads in each of these layers, isn't it? Then we have, you can write K vertical equivalent is nothing but into K vertical equivalent into total head loss by the length of total flow H is nothing but KV1 H1 by H1, right? Is equal to KV2 I2 equal to KV3 I3. Okay, like this up to nth layer KVN IN. Okay, nth layer. Therefore, you can write H is equal to H1 I1 plus H2 I2 plus dot dot plus Hn In. Okay, from here you can write KV equivalent nothing but H by H1 by KV1 plus H2 by KV2 plus dot 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 Hn by. Okay, this is the relation for vertical flow. Okay. Now we studied how to determine hydraulic conductivity. Previously, we studied how to determine hydraulic conductivity in lab. Okay, so how can we determine hydraulic conductivity in lab? It is nothing but using the constant head test or the falling head test, right? So the constant head test is generally used for granular soil, and the falling head test is generally used for uh, this fine grained soil, such as clay, right? It is for lab determination of hydraulic conductivity. Now, how to determine hydraulic conductivity in site? Okay, in site, how to actually calculate hydraulic conductivity? So there are many methods. So one of the method is nothing is this porous probe. Okay, this porous probe. So for porous probe, this K is given by Q by H. So K is nothing but pi d square by 4. It's D1 and H2. So there is the soil. You put some probe inside it, and then you measure the this change in head in there. Okay, so from there you guys actually get this K value. Now that is not actually that important. The important thing is this method, pumping from wells. So this is the very common method that is actually used to determine the in situ hydraulic conductivity. In that, what actually we do is that uh, we make a main borehole. Okay, in the soil, what we do, we make a main well or borehole. Okay, main well we dig, and at some known distances, what we do, we make some more holes, smaller holes. Those holes are actually known as these observation wells. Okay, so in between there are some a main well is drawn, okay, main well, test well, that is known as a test well, that is actually constructed, and at some known distances from that, from the center of that, some observation wells that is constructed. Now what we actually do is that we start pumping out water from this well, this test well. We use machine, we use a pump, and what we do, we start pumping out water from that well till the time the level, okay, the level in this test water level, we keep on checking the water level, okay, till the time this level in this test wells become almost constant. This level does not change anymore, okay, the water level there, okay, the water level in this test well does not change anymore. We keep on pumping out. The point where this gets constant, okay, this depth of water in this test well get constant, there we stop pumping, okay. So after that, so see, here is the this main test well, and here we have two observation wells, okay. So water is actually pumped out from here, okay, till a constant flow rate is actually achieved. This water is pumped out, okay, water is pumped out. Now what will happen? So when you are pumping out the water from the ground, whatever groundwater is there, whatever groundwater is there, that water is actually coming out through the flowing. So water from all water is there in the soil, right? So the water is passing through the pores of the soil. Okay, water is traveling through the pores of the soil, coming to this well, and then it's coming out. Right. So this is actually happening. Right. So what we need to do is that you need to make certain measurements here. The first what you see here, these distances you need to know. So R1 is the distance from the center of the test well to the one observation well. R2 is the distance of the center of the second observation well from the center of the test well. These distances you know, right? Now these heights H1 and H2 you have to measure. So these are the heights of depth, or the heights or the depths of water in the observation wells. Okay, H1 and H2, these also you know. So R1, R2 you know, H1, H2 you know, right? Now, how do we actually do that? So for derivation, what we consider is that, say at any distance r, okay, this is the drawdown. This black curve that that you see here, that is known as the drawdown curve. It is nothing but the shape of the water table when we pump the water. Okay, this is the steady state shape of the water table that you are going to get. Okay, so obviously you are pumping out from here, so the depth will be larger here, and here the depth will be lesser. Right, as we move far away from the test well, the depth will be lesser. This depth will be lesser. Now, say at r distance, okay, say at r distance, we have this height h from below. We have this height h. So what we can write is that the flow of water at any r distance is nothing but k dh by dr. This is nothing but the gradient, nothing but the gradient of flow, right? dh by dr by twice by r h. Okay, why twice by rh? Twice by rh because the water is actually, say, you can imagine a cylindrical something. Okay, so water is coming to the test well from the whole cylindrical section of the soil, right? So that's why twice by r into h. Okay, so now what we do, we integrate this from r2 to r1. So we are going to get k is q ln r1 by r2 by pi h1 square minus h2 square. Okay, so this is what you are going to get. Okay, this is what you are going to get. Okay, so you measured r1, r2, you measured h1, h2. This q is nothing but the constant. This q is the constant flow rate achieved by pumping out water. Okay, from test well. So that is the steady state. Okay, the water we are pumping out till you achieve a steady flow. Okay, steady outflow of water. Right. So this R1, R2, Q, because you are pumping that water out. So Q you can measure, R1, R2, H1, H2 you can measure. So from this you can get this K value. K is nothing but the hydraulic conductivity. Okay. So this is nothing. This is the basic seepage part. Okay, this was all about the seepage part, not seepage, basic permeability part. Okay, how to measure permeability, what is permeability, how do you measure it in lab, how do you measure it in field, all of this we saw. Okay, what is how do you calculate the equivalent horizontal hydraulic conductivity, how do you or equivalent horizontal permeability or equivalent vertical hydraulic conductivity, how we measure all this, we saw this. Okay, this was just the basic. Now the next topic that we encounter, that is nothing but a seepage. Okay, that is nothing but the seepage. So what is seepage? Seepage is nothing but the flow. Okay, how we can actually mathematically define the flow of water. Okay, flow of water through this soil. Okay, so the soil body, how we can mathematically define the flow of water, that is nothing but this seepage, that we will see in this seepage topic. Okay. So the seepage is generally defined mathematically. The seepage or the flow of water through a porous media. Here we are consider porous media is nothing but a soil that is actually governed by the Laplace equation. But it is nothing but governed by the Laplace equation. So what is this Laplace equation? We are going to see. Okay. So say we have a soil mass. Okay. So you can see here this is a soil mass. Okay. Parallelepiped shaped soil mass. So in horizontal direction the uh this is okay, this soil mass is infinite cell size, very small soil mass you are considering. Okay, very small soil mass, dx length, dz height, and dy is the depth. Okay, these we are considering, these dimensions we are considering, dx, dz, and dy. Okay, so so what we can write is that, so actually, in the class, everything was actually done in detail. I think that's why I won't be repeating that. So just I will write the basic. Okay, from the continuity equation, what we can have, the vx by dou x plus dou vz by dou z is equal to 0. Okay. Now what is this vx? Vx is nothing but the velocity of flow in this direction. Okay, in the horizontal direction. So, okay, in this direction. So for one phase you are considering. So this Vx is nothing but Kx. It is the horizontal conductivity in x direction into Ix, right? And we can write Ix is nothing but dou h by dou x. So h is nothing but the head loss. Okay, or the head difference. And dh dou h by dou x will give you the hydraulic rate. Similarly, Vz we can write as, right? So now if we put this here, what we will get is that this is nothing but the Laplace equation. So this you are considering for 2D flow. Okay, say the flow is only taking place in 2 dimensions. So if I draw this like this, so only 2 dimensions you are considering. Okay, if the flow is, so the flow in other direction we are not considering here. Okay, so that's a 2 dimensional plane strain analysis. 2 dimensional plane we are considering this. So this is nothing but the Laplace equation. Kx dou square x by dou x square plus kz dou square h by dou z square. H is nothing but the flow head. Okay, the head loss. Right. Now for isotropic condition. Now for isotropic soil. For isotropic soil, Kx is equal to Kz. That is the hydraulic gradients in both x and y directions, or x and z directions are going to be same. Okay, both in x direction, these are going to be same for isotropic soil. So that's why for isotropic soil you can write. Okay, so this is for isotropic soil. Okay. Okay, now for 1D flow. Okay, so this was for 2D flow. So in two directions, okay, we are considering flow in two directions, but we are saying that this for this case, this is the case that, so this is for perfectly 2D flow, where 2D anisotropic flow, because Kx and Kz are different. And this equation is for 2D isotropic flow. Why isotropic? K is same in both the directions. Now what about 1D flow? So the flow is only occurring in one direction, one directional flow. Okay. For that we can write. So this is the equation. Right. So this is the equation for 1D flow, because we are considering that the flow is only occurring along the z direction. Okay, the z direction. So what we can do? So this one you can easily integrate. So what will be h? Is equal to uh, a1 by a1 to a2, where a1 and a2 are integration constants. Okay. Okay. Now say you have two layers of soil. Okay, this is one, this is two. This height is h1 and this height is h2. Okay. Okay. And the head loss, sorry, and the head here is h1c. Then at any point here, what we can have? We can have hs h1 and at any point here we can have h is equal to okay. So this actually I'm not going into detail because I think this has been discussed in the class. Okay, just so then recall whatever was taught. So that's why he just uh, wrote this equation. Okay, so I am not discussing this because it's, if I start discussing, it's going to take a little bit time, because slowly we have to solve everything, put all the set all the dimensions, and then we have to solve. Then we will see that we are getting all this. Z is in its depth z. Okay. So I'm not going into detail. So these, all of these things are completely done in the class lectures. Okay. Now let us come to flow nets. So what are flow nets? Flow nets are nothing but the solutions of the Laplace equation. Okay, the solution to the continuity equation, that is the Laplace equation, are the flow lines and equipotential lines. The flow lines and equipotential lines, these lines are together, they form a net. So that net is net, so that net like arrangement that those lines form, that is called the flow net. Okay, that is called the flow net. Now, flow net, this this flow net comprises of these flow lines and equipotential lines. Now, flow lines and equipotential lines, generally they have a property that these lines are generally orthogonal to each other. That is, they are always they are perpendicular to each other. So if these are the flow lines, so at all the points the equipotential lines will be perpendicular to them. Okay. If these are the flow line, this is flow line 1, flow line 2. is equipotential line 1, equipotential line 2. So they are perpendicular to each other. That is their orthogonal. So together they form a family of curves, which is nothing but the flow net. Okay, and this flow elements, these element. Okay, here you can see they have formed a square-like structure. So generally they are almost square. Okay, so these are the properties of basic properties of flow net. Okay, okay. So now let us see a flow net for one sheet pile. So say you have a soil, and in the soil you have a sheet pile. Okay, sheet pile is nothing but a type of retaining structure. Okay, say you have a sheet pile. Okay, here you have some head. Say water is there in one side, and the other side you don't have any water. So obviously due to the high head on one side, water is going to flow from one side to other side, right? So that flow of water, that can be how the water is going to flow, how much water is actually going to flow, that we how much water that is going to flow, that we can actually determine by drawing flow nets. So if we draw properly, if we draw the flow nets, taking the scale and following all the rules, we will get what we can do is that we can calculate the amount of flow that is going to take place. So if you take a proper scale, say in a field you have this arrangement. Okay, now you are asked to find out the flow. Okay, how much amount of water is going to seep through the soil to this side, to the downstream side. How we are going to do it? So one easy way to do that is this. What we can do is that we can draw the draw everything to scale and then construct the flow line. So there are flow nets. Okay, so there are various softwares also which are available, which actually help in construction of this flow net. So if we construct the flow net, this flow net actually give us a means to calculate the amount of flow or the amount of seepage of water that is going to flow happen or that is going to occur. Okay. So if I want to draw the flow lines, this will be something like this here. Okay, in that case, 1, 2, 3. Okay, then we will have the equipotential lines. This, okay, something like this. We will have a equipotential line. So all this, so this is a equipotential line. This is always remember that this is a equipotential line. This is a equipotential line. This is a flow line. This boundary is a flow line. These boundaries are equipotential line. Remember, these boundaries are equipotential line. This boundary, the bottom boundary is a flow line. These are the flow lines. These are the flow lines. Okay, and these are the equipotential lines. Okay, so and these are always perpendicular to each other. Okay, these are always perpendicular to each other. These are always perpendicular to each other. All right. So these are the flow lines. These are the equipotential lines. Okay. Now let me draw just a second. 1, 2, 3. Yeah. So can you find out the number of flow channels? So what are flow channels? So now one more term let me see flow channel. So what is a flow channel? Flow channel is nothing but the channel that is made by two flow lines. Two adjacent flow lines make a flow channel. Okay, these are the flow channels. So here if you see in this diagram, the number of flow channels can be is 4. Okay, and what are the number of equipotential drops? That is from 1.1 equipotential line to the other equipotential. How many of these drops are actually happening when you traverse across a flow line? When you traverse across a flow line, how many of these points, how many of these junctions are you encountering with any equipotential line? That is the number of drops. So here to here, one drop, here to here, two drop, right? Here to here, three drop, here to here, four drop, here to here, five drop, here to here, six drops. So total six number of drops are happening. So while we are traversing across this uh, equipotential line, we are first, so from this is as I said, this is the equipotential line. So from here to here we are traveling, right? So this one drop. Again from here to here, one more. So second drop, third drop, fourth drop, fifth drop, and sixth drop. Total six drops, six number of potential drops are happening. So you can write that this ND, this number of drops is nothing but six. Okay, this is very important because we use this NF and ND, number of flow channels and number of equipotential drops, to determine the flow that is happening. Okay, determine the flow that is happening. When we solve the problems, this will be clear. Okay? Now still, so let me just uh, draw a zoomed view of, say, a flow channel. Okay, so say this. So this is the green is the flow line, and the red is the equipotential line. Okay, green is the flow line, and the red are the equipotential lines. Right. So obviously these are, that's why perpendicular. Okay, so perpendicular. Now let's say delta Q flow is actually happening through each potential drop. So not potential, each flow channel. So through each flow channel. So this is nothing but a flow channel. Okay, this total area. This is nothing but a flow channel. Right. So this yellow part is nothing but a flow channel, right? This yellow part is nothing but a flow channel. So through this flow channel, delta Q amount of water is, or fluid is flowing. Right. Now this delta Q will be equal to delta Q1 is equal to delta Q2 equal to delta Q3 is equal to delta Q1. Right. Now each delta Q we can write as K. So now we are considering isotropic soil. Isotropic soil, how is it isotropic? Because K in horizontal, vertical, all the directions, the hydraulic conductivity is same. Hydraulic conductivity is independent of direction. That's why we are just writing K. So K H1 minus H2 by L1, okay, into B1 into 1. So let me write this. Now, this is L1. Okay, similarly, this is L2, and this is B1, and this is a B2. Okay, now L1 is nothing but the length, and B1 is nothing but the width of this one, this square that we are saying. So since we said that these are generally square, so we are to draw the flow net in such a way that this boxes that are formed, these are square. So that we need to ensure while drawing a flow net. This we need to ensure that always these are squares. So if these are squares, so K, what is Q? Q is nothing but KIA. So K is the hydraulic gradient, not hydraulic gradient, hydraulic conductivity. I is the hydraulic gradient. What is hydraulic gradient? Head loss divided by the length of flow. So what is the head loss? Say head loss. Head here was H1. Then when the water flow from head here is H2, then it is H3. Say. Okay, like this it's falling. So the flow in this part is, we are saying it is Q1, say. Here it is saying Q2. So in all these small boxes, this Q is going to be same. That's why we wrote this, because of the continuity equation. This flow is going to be same, obviously, in a flow channel. All these Qs are going to be same in one. I am talking about one channel. In one flow channel, this is one yellow, total yellow part is one flow channel. This one flow channel is composed of two these boxes. So in one box, we are saying this is Q1. Is Q2. Okay, this in that box the flow is Q2. So all these Qs are actually equal. So this is one relation. So any Q is equal to K. Okay, K delta Q1 equal to delta Q. Everything is same. All Qs are same, equal to K it times the head loss. So from here to here, head loss is H1 minus H2. So it was H1, then it came to H2, came down to H2. The head loss head. H1 minus H2 divided by L1. L1 is the length into the area cross. So area of flow is nothing but this uh, dimension times the other out of plane direction dimension is out of this screen, out of this direction, that we are considering one. The dimension perpendicular to the screen or to the computer screen is the out of plane direction, that we are considering one. So b times 1. So this, if it is square, so sin square b1 is equal to L1. So we can write K H1 minus H2 by L1 into L1. Right. So right. So K into H1 minus H2. Done. Now there are several head drops that are considering, right? So H1 to H2, then H2 to H3, like this, several head drops are there, right? So like this, several head drops are actually occurring, right? From here to here, to like this. Several head drops are actually occurring, isn't it? There are several head drops that are taking place. Now this say H1 minus H2 will be equal to H2 minus H1. This all these head drops we can equate to H by ND. Capital E is nothing, H is nothing but the total amount of head that is dropping from entry to exit part. Okay, so this we can write as K into H by ND. Right. So this is the delta Q for one flow channel. Right. So this is the flow through one flow channel only. This is flow through one flow channel only. One flow channel. Okay, one flow channel only. Like this, several other flow channels are also there. Right, other flow channels also be there. So what will be the total flow? Total flow will be nothing but delta Q into the number of flow channels. Simple. So Q is nothing but KH NF by ND. So this will give us the total flow. Okay, so this will give us the total flow. Okay. All right. Now, uh, let us start solving the problems. Okay, let's start solving the problems. So you can see the problem here. These are, so we will be solving very easy and simple problems. All right. So these problems are very easy. The first problem is a horizontal stratified soil deposit contains three layers, each uniform. So each layer is uniform. Okay. The permeability of the layer are 8 into 10 to the power minus 4, 50 into 10 to the power minus 4, and 15 into 10 to the power minus 4 centimeter per second. And the thickness of each of these layers are given. Okay. So we have to find out the effective permeability in the horizontal vertical direction. So it's very easy. So we already so saw what the expressions are for the equivalent horizontal permeability and the equivalent vertical permeability, right? So we can easily solve this. So just try for 2 minutes how to uh, just try to solve this. Okay, just try to solve this. All right, just give me a second. Yeah. So let me just draw it for you. So we have three layers. Like this, we have three layers. Okay. So thick, all have different thicknesses. 6 meter, 3 meter, 12. All right. And the case for all the layers are also given. So for horizontal flow, thing but kx is equal to by h1 plus h2 plus h3. Okay. So what is k1? So this is going to come out as 10. Then for vertical flow, the vertical flow Ky is nothing but h1 plus h2 plus h3 by h1 by k1 by k3. So if you put all the values, 6 plus how much? 6 plus 3 plus 12 by will come out as 13.04. So if you compare these two values, is 18 and this is 13. So generally K horizontal equivalent is greater than K vertical equivalent. Okay, generally this is the case always. Horizontal is greater than the vertical. Okay? Always this will happen. Right? So very easy, just all the values are given. So directly we can use the expression that you realized. Okay, for horizontal flow and for vertical. The soil layers below have a cross section area of 100 mm into 100 mm each. The permeability of each soil is given. Find the rate of water supply. I will just draw the diagram. Okay, just draw the layers for you. This is soil layer A. This is soil layer B. This is soil layer C. Okay. 3. And the head difference. Okay, the head difference between entry and exit is 300 mm. Okay, this is 300 mm. Now each one is given as 150 mm. These are given values. Okay, H2 is given as 150 mm. All are same. H3 is given as 110. Where A, B, C. It's better, na? A is given as this. All right. Okay. Now the water is actually flowing like this. Right. So here can you say that what we are going to use the expression for horizontal flow or the expression for vertical flow? What we are going to use? Can you tell me which expression we are going to use here? Whether is it the expression for horizontal flow or is it going to be the expression for vertical flow? Horizontal flow or vertical flow? This looks like a horizontal flow, but is it actually the horizontal flow case? What is happening? In each layer, the flow is going to be same, right? The flow is going to be same, but the head loss is going to be different in each layer. Right, the head loss is going to be different in each layer. So this is which case, horizontal case or the vertical case? So this is nothing but similar to the vertical case. Right? So vertical flow was like this, right? So the flow Q value in all this will be same, but the amount of head losses in different soil will be different, obviously, depending upon the value of K. Right, so we need to use the expression for the vertical flow. So K equivalent is nothing but same. K3. So if we use this, this will come out as 1.2 into 10 to the power minus 3 meter per second. Okay, just put all the values, all the given values, you will get the result. Okay, so the main tricky part is that this looks like a horizontal flow, right? This looks like as if the flow is horizontal, but the uh, uh, actual case is that the flow is actually vertical. This looks as if it is a horizontal flow, but if we see it properly, if we see how the flow is actually happening, that is the case of vertical flow, right? This vertical equivalent case, correct? So if we have determined K equivalent, the thing it is just the find the rate of water supply. So how can we calculate the rate of water supply? Nothing but Q is equal to K equivalent I into area. So it's 1.2 into 10 to the power minus 3. What is I? The total head loss 300. Length 150 plus 150 power 150. 450 into area. This is 10 centimeter into 10 centimeter. It's 29. and cm cube per hour. Okay. Okay, so this will be the rate of water supply. Okay. Next, the following data uh, were recorded in a constant permeability test. So details about a constant head permeability test are given. Internal diameter of permeameter is given. Head loss over the sample length is given. Quantity of water is collected in 60 seconds is given. Porosity of soil sample is given. We need to calculate the coefficient of permeability, discharge velocity, and seepage velocity. So three things we need to determine. First, we will determine obviously the permeability of the soil. K. Right. So this is the case of constant head test. So in the constant head test, if you remember, there was a soil sample. Across the soil sample, a constant head was maintained, and uh, and we collected some amount of water, some volume of water in some given time. Using that value, okay, using that Q value, that is the amount of water connected in some time t, that flow rate is calculated. Using the flow rate, we calculate the K, right? So what is the area of the sample? Pi by 4 into 7.5 square is nothing but 44.18, right? And what is the height or the length of flow? That is the length of the sample across which the flow is occurring, the length of the sample along which the flow is occurring, right? That is 24.7 centimeter. Okay, so sorry, this 24.7 is the head loss, not the length. The length is 18 centimeter. This 24.7 centimeter is nothing but the head loss. Oh, that is the head, the constant head that you are maintaining. Okay, constant head that you are maintaining. That is 24.7 centimeter of head you are maintaining across the sample. The length of the sample or the height of the sample is 18 centimeter. Okay, the time in 60 seconds we are collecting 626 ml. Right, it's the Q. So what will be capital Q? Volume by time. So 626 by 60. This is ml second. If you convert it to centimeter, it will be 33 centimeter cube per second. Okay, this is the flow that is happening. Now, what is the hydraulic gradient? What will be the hydraulic gradient? Hydraulic gradient is nothing but head divided by the length of flow. So what is the total head here? Constant head here, 24.7 centimeter. So it will nothing but h by l, 24.7 divided by 18.372. Okay, this is the hydraulic gradient. So now you know that flow is nothing but KIA. K is Q by IA. Q we calculated how much? 10.433. I is 1.372 into area. What is the area? 44.18. You put all the values, will get KS. So calculated the coefficient of permeability. Next is the discharge velocity. What is discharge velocity? V is from Darcy's law. V is equal to KI. So 0.172 into 1.372 will come out as 0.236 centimeter per second. Now the last thing is seepage velocity. So this seepage velocity we discussed in the previous class. What is seepage velocity? Superficial velocity or discharge velocity by the porosity. Right? We'll give the seepage velocity. And the seepage velocity is always greater than the superficial velocity or the discharge velocity. Per second. So Vs is always greater than T. Alright? So this was it. Now similar problem we are going to solve for falling head test. So we solved the problem for constant head test. Now let us see for falling head test. So in falling head permeability test, The head is constantly dropping with time. As time passes, the head keeps on falling. But in concentrated test, with constant supply of water, that head is maintained. Okay, constant head is maintained across the soil. That head does not fall with time. But in this test, but in this falling head test, the head loss keeps on changing. Okay, this head keeps on falling. But in concentrated test, the constant head difference is actually maintained. So how to solve for falling head test? We already derived the equation. So just let us just see what values are given. So initially head was 90 centimeter and then it drops to 6 centimeter in time 15 minutes. Okay, okay. It's given it drops by 6 centimeter and it drops 6 centimeter. So H2 is not 6 centimeter. It drops 6 centimeter in time. Okay, it drops 6 centimeter in time 15 minutes. So H2 will be nothing but 90 minus 6, 84 centimeter. All right. Now we have K. We derive this equation. Ln, if you convert it to log, it will 2.303 AL by 80 log by. So what is given, what is asked, how much time is required for the head to fall to 45 centimeters. So we are not asked the coefficient of permeability here. Instead, we were asked how much time is required for the head to fall to 45 centimeters. Isn't it? How can we do that? So here, from here, we can write 2.303 AL by K into A is nothing but T by log H1 by H2. We put the values 15 by log 90 by 84. So this will come out as 500.61. Okay. Now what we do, so this one you got, this is equal to this. Right, this you got, this constant value is equal to this. Now what we do, H1 is 90 centimeter. Now it is asked when H2 is 45 centimeter, what is the T? How to get that? Same. T is nothing but 2.303 AL by KA. Okay, H1 by H2. So this one you already know from here. So write the value. Like 45. So this is going to be 158. Okay, this is how we do this. So in one case is given, the first case initial head was 90 centimeter, then in 15 minutes it drops to 84 centimeter. So from using that we got the constant part. Using that we can find out when the head will fall to 45 centimeter, how much time will actually get elapsed. Okay, so this much time. Okay? Okay. Let us see this. A wall penetrates an unconfined aquifer having a saturated depth of 100 meter. The discharge is 250 liter. A well penetration unconfined aquifer having a saturated depth of 100 meter. The discharge is 250 liter per minute as a 12 meter drawdown. Assuming equilibrium four conditions and homogeneous aquifer, estimate the discharge at 18 meter drawdown. So what is a aquifer? What aquifer is nothing but a type of soil which holds large amount of water. That is called an aquifer. Unconfined aquifer means that confined aquifer means between two impervious surfaces, we have a soil which holds water. This is a confined aquifer. What is an unconfined aquifer? Unconfined aquifer is that this is not confined. Okay, in between two impermeable. Okay, so here we have a well. Okay, so say this is the soil surface. Okay, we have a well. Okay, saturated depth that is given as, so we are pumping out water and so this saturated depth is 100 meters. Discharge that is coming out from the well, that is 250 liters per minute at a 12 meter. Okay, so at 12-meter drawdown means from what how to say, uh, mm, when the depth of the water, okay, when the depth of the water from the initial surface, okay, when the depth of the water from the initial surface is 18 meters, 12 meters, that time this is the discharge. Okay, to 50 meter. Okay, we need to estimate estimated discharge at 18. When the drawdown will be 18 meters, at that time what will be the discharge, that we need to find out. Okay, that we need to find out. So if I okay, so at 12-meter drawdown, so when the water is here in the well, at that time 250 liters per minute is the discharge. We need to find out the discharge when this water level will drop down to further, it will drop down to 18 meters. Okay, we need to find out the flow at that time. How do we do this? So for a unconfined aquifer, K is actually given by 2.303 Q log R by R naught by pi h square minus h naught square. Okay, this is the expression. Okay, for an unconfined aquifer. All right. In that case, if we put all the values, you will get pi k by 2.303 log 10 r by r naught is equal to q by h square minus h naught square. So what is q 250? What is h initially? H is nothing but the this depth of water. Okay. Initially it was 100 meter was the saturated depth. 100 minus h naught. So h naught now first case h naught is minus 12. 100 minus 12. 100 minus 12 nothing but 88 meters. 8 square. It is 250 by 2256. Okay. Now second case is when h naught is 100 minus 18. It is 82 meter. At that time we need to find out the flow. So pi k pi k 2.303 log r by r naught. So this one you already know from here, 250 by 2256. 2 Q2 will get the flow as 363 liters per minute. Okay, so obviously you are pumping more water out, right? So the water depth has gone farther below. Okay, this is how we have to do this. Now let us solve a problem similar to whatever we discussed before, right? Similar to what means that, well, there are test wells. That case, let us see here. Okay, similar to. So a 30 centimeter dia well penetrates to a depth of 25 meters below the static water table. Okay. So say this is the static water table. So there is a well that penetrates 25 meters below the static water. This is after 24 hours of pumping at a constant rate of 5,400 liters per minute. Okay. Yeah. So 25 meters, right? Now, after 24 hours of pumping at 5,400, the water level in the test well at 90 meter is lowered by 0.53. Means at a distance of 90 meter, we have a test well. That is okay. So at a distance of 90 meter, you have a first test well. So in this test well, the water is lowered by 0.53 meters. Means the water is here. And in another test well, which is 30 meter away, here the water is obviously it will be lowered more, right? So here it is 1.11 meters. All right. So this R1 you know, R2 you know. Okay, let me write down. So H is 25 meters. So this saturated depth, this depth is 25 meters. R1 is 30 meters. R2 is 90 meters. What is H1? H is nothing but a height, right? The drop means the total height minus the drawdown. H1. So what is the total at 25 minus the drawdown 1.11? Will be 23.89 meters. And what about H2? Same 25 minus 0.53 is 24.47 meter. Done. H1, H2 we have, R1, R2 we have. So already we derived the expression. So this Q is nothing but 5,400 liters per minute. So this one, if we convert it to meter cube per second, it will be 0.09 meter cube per. Okay, we derived this already. 3.0 Q log R2 by R1 by pi H2 square minus H1 square. So Q you know 0.09 given, R2 you know. What is R2? R2 is 90, R1 is 30, you know. Pi H2 you already know. H1 you already know. So you can get the K value, permeability value. It will come out as done. So just directly by putting the expression, you got the value. Now, one thing is what is the transmissibility of the aquifer? So K, that is the permeability or the hydraulic conductivity you got. How to find out the transmissibility? Transmissibility T is nothing but K into the total height. Total height of the water table, saturated water depth. Okay. So K is 1.121 into 10 to the power minus 3 into what is the height? How much? 25 meters. 25. So it will be 0.028 meter square per second. Done. Okay. So let us see the next problem. The coefficient of permeability of fine sand is 0.022 centimeter per second at a void ratio of 0.72. So at 0.72 void ratio, this is the coefficient of permeability. Estimate the permeability of the soil if the sand is compacted to a void ratio of 0.57. This is a carbon formula. Okay. So obviously, if the void ratio is reducing, you can expect that the uh, soil is becoming more dense, right? The sand is becoming more dense. So if the soil is becoming more dense, the permeability is going to reduce, right? So the quasi-Kalman formula is nothing but K is C into U by 1 plus E. Okay, this is the main basic formula. So K1 you can write as C into E1 Q by plus E1, and K2 you can write as C2, right? K1 by K2, right? E2 cubed by plus E2, right? 0.022 by K2 is equal to how much? 0.72 cube by 1 plus 0.72 divided by 0.57 plus 0.7. Okay. So if you do this, you can get K2 as 0.012 centimeter per second. So as expected, you can see that with reduction in void ratio, the permeability is also reducing as expected, right? Okay, let us see the next problem. Okay, just give me 1 minute. Okay, so this one we already solved in the previous class. So this one let us solve. Okay, this case one is already done in the previous class. So case two, please just try for 2 minutes. How we can proceed. If we have done that, it's fine. Well and good. I had still told to do this as a homework, right, in the previous class. So try to solve that again now. If you have done well and good, so I'm going to solve this again. Okay, this is case two. Give me 2 minutes time. Okay. So if you remember, this question was nothing but we need to determine some heads. Okay, the pressure head, the total head, all these heads, the pressure head, elevation head, total head. Okay, all these things we need to determine the entry exit points and the point A. Okay, so for that, what we did, we just made a table, right? So just make that table again. So first we can write this is a uh, point, then elevation head, pressure head, total head, and we have head loss. So first is nothing but the entry point, right? So zero is the entry point. So water is head here is high, right? Head here is high, head here is low, obviously. Okay, you can see. So there is the entry point. So this is 0 point, this is the entry point. Then we have the exit point. Exit point is which one? Fourth point. Then we have fifth point. Then we can find out the A at the A point. So at 0 point, what is the elevation head? If we consider that is 0, if we consider that as the datum only, so we can write it as 0. What is the pressure head? Pressure head is this much, 9. 9, so total head is 9. Elevation head plus pressure head gives a total head loss is 0. Now at exit point 4, here, what is the elevation head? It is 4. What is the pressure head? 1, right? Here, 1. Total head 5. What is the head loss? What is the head loss that is happening? It is head loss happening is 4. Right? Traveling from here to here, 4 amount of head loss is happening. Right? 4 meters head loss is happening. Now let us come to fifth point. Elevation it is 5. Pressure head is 0. Is 5. Same head loss. Head loss will be same here. Now you need to find out A. In order to find out the point A, we find the hydraulic gradient. So how much head loss is totally happening? 4 meter head loss is happening across what length? Across this much length head loss is happening. So 4 meter head loss is happening across 4 meter length. So hydraulic gradient is 1. Therefore, for 1 meter, okay. Therefore, for 1 meter, how much head loss will be happening? I into 1, that is 1 meter, right? I into 1, that is 1 meter. For traveling for traveling 1 meter distance, for as the water traverses 1 meter distance, how much head loss is happening? I into 1. It will is nothing but 1 into 1, 1 meter. So that is the head loss. So head loss is 1. Total head will be how much? Obviously 8. Have to be 8. What is the elevation head? I know 1. So obviously pressure head has to be 7. Okay. So this is how we calculate the elevation head, pressure head, total head at all the points. Fine. Done. Now one more. Yeah. Done. Now one more thing we need to calculate what are the superficial and seepage velocities. So how do we calculate the superficial velocity? V is equal to AI. What is K? K is given 0.1 in the question and I is nothing but 1. 0.1 meter per second. And N is given in the question 3. So what is the seepage velocity? 0.1 by 0.33 centimeter per second. Okay. Done. Very simple. Let us come to this problem. So two soils A and B are arranged in the manner shown in the figure. Okay. So you can see there are two soils, okay, arranged one above other. And flow is obviously, how is the flow occurring? Flow is obviously occurring. You can see in this case the flow is occurring in this direction, right? Like this the flow is occurring. The dimensions are also given, elevations are given. So what we need to do, determine the quantity of flow. So we need to determine how much flow is actually occurring. The K values are given. It is the uh, this hydraulic conductivity values are given to us, isn't it? Is that given to us? Now, how to solve this? How to solve this? So one way can be directly you can say that this is the case of a vertical flow. So directly what we can do, we can determine the K equivalent H by H1 by A1 plus H2 by K2. Like this you can determine. So what is H 03? 1. So if we do this, K equivalent is going to come out as 0.0181 percent. Okay, then you have to determine the quantity of flow. The flow is nothing but Q is equal to KIA 0.181 into I. I is what? I is the total head loss. How much is happening? Elevation total head loss is how much? Mm, just a second. Yeah, total is 4.5, right? 4.5 by 3. Right? A 1.5. Okay, 1.5 meters into minus 2. This we do, we will get 4.1 plus 4 meter cube per second. Okay, this is the simple normal directly by using the K equivalent thing we determine. But if you want to really understand this, what we can do is that we can calculate the flows at each soil A, soil B, then we can add these flows, and like that we can actually find out. So that way if you do, it will be actually a little bit more clear to you. So how do you do that? So see, the flow rate in soil A will be equal to flow in soil B. This is one we know. This is this has to be okay. This is one condition that has to be followed in this case, right? Obviously, water entering here is obviously water leaving and entering the other. Same, right? So flow is has to be same. Now at elevation 3 meters, what is the total head here? Elevation head is a 3 meter, pressure head is 1.5. So 3 plus 1.5 is 4 meter. Now at elevation 0, what is the total head? Nothing but 0 plus 0, 2 meter. Done. Now this is 4.5. Yeah. So this 4.5 is what? The 4.5 is the total head loss that is occurring while the flow is happening from here to here. Now this 4.5 is the total head loss. So out of the 4.5, some head loss is happening in soil A, and some head loss is happening in soil B. Right? Is nothing but head loss happening in soil A and head loss happening in soil B. So this is one relation. Okay, this 4.5 obviously should be equal to so head loss happening in soil A plus head loss happening in soil B. Done? Done. Now as QA is equal to QB, okay, as QA is equal to QB, we can write VA is equal to VB, or we can write KA into IA is equal to KB into IB, right? Therefore, AA into HA by 1.5 is equal to KB into HB by 1.5. Done. Therefore, HA by HB, we can write it as KB by KA. So what is KB by K? KB by K is given. So KB by KA is nothing but 0.1. So here from here you got one relation. So HA by HB is equal to 0.1, and one more relation is HA plus HB is equal to 4.5. From here you can get HA and HB. So if you use these two, equation 1 and equation 2, you can get 1, 2, you can get HA is equal to 0.41 meters and HB is equal to 4.09 meters. So you can see out of 4.5 meter total head loss, 0.41 meter head loss is occurring in the soil A. Okay, in the soil A. and other 4.09 meter head loss is occurring in the soil B. Now, if you want to relate this, head is what? Head is nothing but energy. So see, soil A has higher permeability. So the water can easily flow through it. So less amount of energy is consumed while the water passes through soil A. But soil B has 10 times less, as soil B has 10 times less permeability than soil A. That is, while the water passes through soil B, more amount of energy will be required. Right. That's why you can see more amount of head loss is happening in soil B. Right. Right. Now, easily you can find out, first you can find out Q, same QA will be equal to QB is equal to Q is equal to say KA. So what is K? K is 0.1 is IA will be I, A will be nothing but same 1.5. Okay, this will give the same answer 4.1 into 10 per minus 4 meter cube per second. Okay, the same result. See, same here also you are getting 4.11. So like this also you are getting 4. Okay. Okay, now let's come to this. So this is quite similar to the previous problem. So just try for 2-3 minutes. Just try by yourself how to solve. Let's see. Okay. So this is also quite similar, but here what is happening is that the soil flow is occurring simultaneously. Okay, in both the soils, flow is occurring simultaneously. Right, the flow is occurring simultaneously in both the soils. In this case, okay. Here, let us see how we can actually do. So, if you see this is quite similar to the this H case, right? Horizontal flow case, right? So, similarly, what we can do, we can use this formula for relation that we already derived. Point 0.055 centimeter per second. Therefore, so total, what will be the Q? Q will be K I is A 1.2375 into 10 to the power minus 3 per second. The same. Okay. Similarly, what we can do for this one also, you can solve it in the other way around. similar to what we solved in the previous case. So if you want to solve it like this, so you can say the total Q will be what? QA plus QB. We need to determine QA and QB. I need to determine QA and QB. So what is the thing that is going to be the same in both the cases? Same will be the head loss. So here HA is going to be equal to HB, right? Which is nothing but 4.5 by 4.5. This is the there is the same amount of head loss that will be occurring in both the soils, right? Here the same amount of head HA will be equal to HB. So if you want to find QA, KA, IA, AA. So KA is given to you. I, what is I? I will be HA by the length of flow is 0.75. If we do, we will get QA. Similarly, you can get QB, and then the total Q you can get by QA plus QB. So to QA plus QB, the total. So this was all for today. So all the problems were actually quite simple. So fine. So I hope everything was clear to you, right? Okay. Right. So with this, we will end today's session. So I hope it was fine. And the next session will be on 22nd of February. Sorry, I think it's 22nd or 23rd February, actually. 23rd February, same time, 6 p.m. to 8 p.m. All right. So thank you for attending. Have a good day.